So today we will continue the chapter 3. Last time we talked about the pumping power for the hydrostatic theory. So this pumping power is from the pressure supply system, the oil supply system. So the equation to calculate the pumping power is supply pressure multiplied by the volume flow rate of the lubricant. So this is the equation to calculate the total pumping power for the oil supply system. So the supply pressure for the oil supply system multiplied by the total volume flow rate of the hydrostatic theory. So if you have more than one bearing pad in your system, so you need to adding together the volume flow rate for each individual pad. So we also talk about the pressure ratio. Maybe this is the pressure ratio for the hydrostatic bearing. So the recent pressure divided by the supply pressure. Okay. This is for the hydrostatic bearing, the data value. So we also have a pressure ratio for the air bearing. This is for the air bearing. So it's also the recent pressure of the air bearing minus the atmosphere. So divided by supply pressure minus the atmosphere pressure. And also we talked about the friction power for the bearing speed. Bearing speed. Okay. So for the hydrostatic bearing at service, if you are moving in very high speed, it may generate a lot of friction heat on your bearing speed, bearing surface. So this is the equation for the friction force for the bearing surface. The eta is the viscosity of the lubricant. AX is the friction area of the bearing. U is the velocity of the moving speed for your hydrostatic bearing. And H is the film gauge thickness. Okay. So for the friction power is the friction force multiplied by the velocity. So it may equal to this eta multiplied by the A and the U squared divided by H. So this is the friction power for the hydrostatic bearing. Similarly, if you have more than one bearing pad, the friction power for each individual pad should be acting together. Okay. If you have your machine tool system, you have three hydrostatic bearing pads. So you need to calculate individual friction power for each pad, and then summarize it together in these three pads. So you have a total friction power for the hydrostatic bearing surface. Okay. So we are using the pumping power and the friction power, pumping power HP and the friction power HN. To define the low speed or high speed, so low speed or high speed hydrostatic bearing. So this one is in another configuration for the bearing pad. Okay. So here we define the power ratio K, which means it's friction power divided by pumping power. Okay. So this is the index to know if the hydrostatic bearing is in high speed or in low speed regime. So from the well, temperature rise of the bearing surface into the moving speed. So the temperature rise is proportional to the K value, the power ratio. Right? So it's the friction power divided by the pumping power. The K value is increasing, which means this bearing is going to have a temperature rise while they are moving. Okay? So we define this K power ratio K. If K is greater than one, uh, it says the high speed hydrostatic bearing. And if the K is smaller than one, it is for the hydrostatic bearing, it's a low speed bearing. So this is quite important in the hydrostatic bearing design. So, if the friction power is higher, bigger than the pumping power, which means the friction heat generated from the bearing surface is greater than the heat generated from the pump, oil supply system. So we're going to summarize here. Okay. So for K is between 0 to 1. This means the bearing is in low speed bearing. K is equal to 1 to 3, which means it is high speed hydrostatic bearing or aerostatic bearing. Okay. And for K equal to 3 to 9, this is in high speed hybrid blend hydrostatic bearing or aerostatic bearing. So this is just the classification for the power ratio, which we can distinguish the hydrostatic bearing, the low speed or high speed. And also, last time we talked about temperature rise and the acceleration of the temperature rise for the hydrostatic barrier. When we talk about the temperature rise, only concentrate on the oil hydrostatic barrier. For the air barrier, the air is carried to the atmosphere, so usually the air barrier, we assume the temperature rise is not so significant. Uh, So for the hydrostatic barrier, this temperature rise may lead to a very large amount. Okay? So maybe during the operational status, the hydrostatic, or the temperature rise for the hydrostatic barrier could be 20 to 30 degrees Celsius. Okay? So in that case, usually we need to have a coolant system in your oil supply system. Okay? So we have this assumption. We assume all the heat generated from the friction power will go to the oil lubricant. Okay? So this is just a calculation for the temperature rise for your oil lubricant. So 100% of the friction power is going to the oil lubricant. Okay, so this is a bit strict assumption. So for the temperature rise integrated by this equation, this means it's overestimate for the critical situation. Okay? So in critical situation, some of the heat will be radiated to the atmosphere or will be contact to the various structure. So the heat will not go to the lubricant 100%. Okay? So by using this equation, it's a bit overestimate for the temperature rise in practical situation. Okay? So by using this, this is total power. The total power being mentioned. Total power is equal to the here. Here's the total power. It's the pumping power plus the friction power. So this is the total heat generated from the hydrostatic bearing system. So both in the bearing pad and the lubricant supply system. So this is the total heat generated from the system. So by using this equation, we can estimate the temperature rise for your oil. So the C is the specific heat capacity of the lubricant. The rho is the density of the oil. So by using this equation, you can have a closed form formula for your temperature rise, delta T, using this equation. And we also substitute the pumping power equal to PS multiplied by Q. So the Q was divided and so you have PS on the top. Yeah, you have finally you have this form of equation. 这个是我们估算出来的温升。我们温升的话是把所有的热量都跑到油里面，当然这个是高估的，因为我们的系统里面的热或者摩擦热我的胖子产生的功率，一些热量，其实有一些会辐射到空气中，有一些会传导在中层的结构上面，所以热量其实不会100%跑到传递到油里面，所以算出来这个 delta T 是高估的，实际上的话会比这个 delta T 低，但是这个就是最糟糕的状况。So we can use this equation to calculate the temperature rise for the oil in the operational state. 所以这个在操作的时候，可以估算它的温升。So the pumping power and the friction power calculation is very important because we want to know the total power generated from the hydrostatic bearing system, so that we can design or choose a correct refrigerator in your pressure supply system to cool down your oil loop. So we need to know the total heat generation or power generation for the hydrostatic bearing system. So here we have different results for different assumptions. So K equals to 0, we define the low speed bearing with the temperature rise using this equation. So K equals to 0, so this one is 1. So we have a delta T equal to PS divided by rho multiplied by B. Okay. So if we know the numerical data for each constant, then we can calculate the temperature rise from the bearing system. So here we have also some example here. Just let you know the temperature rise. Okay. For K equal to 1, the delta T is equal to 1.1 multiplied by 10 minus 6. And K equal to 3, the delta T will be equal to 2.2 multiplied 10 over minus 6. Okay. This is for the high speed bearing. So that for the definition of the power ratio is the K greater or equal to 1. It's called the high speed bearing. K is smaller than 1. It's called the low speed bearing. 这是我们定下来的 分类，k 小于一的话是低速的走，k 大于等于一是高速。So then for the design for hydrostatic bearing, we have objective function, how we can design our bearing. So this is one of the criteria. So if you want to have minimum power consumption for the hydrostatic bearing and the design constraint. So here are some of the discussions. Okay. So the criteria is the minimum power. Okay. So usually we need to have some objective in your design of the bearing system. In this case, the objective function is the minimum power consumption, which means the total power should be minimum. So we have different assumptions here. For the low speed, again, for the low speed bearing, we assume k equals to 0. And k equals to 0, then we have this total power, HP. So originally, total power is equal to HP multiplied 1 plus K. So K equal to 0. So this one is HP. So, and then we have to optimize the bearing at dimension for the goal of the minimum power in this case. This is the ratio of power to the load support. How many power to the total power to the load support here. Then we have this equation. If we assume this B bar divided by A squared bar equal to the H bar. Then we have the maximum load for the minimum power. So the language we can minimize the HB bar. This you can see in your textbook page 53. one of the examples. You can design your bearing system for the medium power and maximum low capacity. Okay. This low capacity is maximum. Then this HP will be smaller because the W is the maximum. So this HP divided by W will be minimized. Okay. So this is one of the design criteria when you design your hydrostatic bearing. Okay, later we will discuss in detail when we see the example. And next, we will discuss the design of the bearing parameter. 下面这个就是设计的细节，就是我们怎么去设计我的静压总值的尺寸，它有一些规律、规则的。So we have this optimum bandwidth ratio. What is the bandwidth ratio for the low speed bearing? So we have we have an example for this here. The language A, the language 外边的宽度跟它的长度是0.2。Yeah. You can look at the example here. This is a bearing seal，这是风油边，这是我的路由槽，这是我的风油边，这是我的边长，所以我们取这个边 A 的尺寸跟 L 的比值是1/4。Okay. Because when you design the bearing, the hydrostatic bearing, some of the design parameters you should define beforehand. 当我们设计这个尺寸的时候，有些的尺寸我们需要预先给定。像风油边的话，就是有一个规定，就是我们选风油边就是它的宽度跟它的长度的比就是1:4，4/4，4/4就是1.25。Okay, so the optimal bandwidth ratio for rectangular 矩形的油腔来讲的话，风油边的宽度，这个就是风油边 ，length 就是我们讲的风油边，我们是叫 seal。You can see the different color in different texture. Some of the books call it length. Okay, length means folio and seal. Width 就是它的宽度啊， 分之一，圆形平面轴的也是一样，这个的宽度是整个这个这个直径的四分之一。这个是油墙，这个宽度是整个直径的四分之一。所以如果是你一开始设定的话，就是要设定这样。这其实是有理论分析过，就是它的摩擦功率是最小，后面就把它定成是那个设计的准则这样。这个手紧轴承也是一样，或者 John Rolling bearing is the same. In the actual direction, the bandwidth A divided by the journal length L is equal to 0.25 quarter. So this is the first guideline for the circular bearing that is the same. Okay. The language ratio is equal to the quarter of the diameter. So this is a baseline for your language ratio design. But in some case, for example, you have extremely high speed innovation. So in that case, you will generate a lot of friction power. So sometimes in this kind of a situation, you can reduce the bandwidth, which means your bandwidth will be smaller than the 0.25. Can be smaller, okay, 0.20。当然，这是一个准则。那有些时候的状况，比方说我的转速非常高，我的摩擦功率非常大，我要降低摩擦功率，我就把 A 这个风流变的宽度的 length 小于这个0.2，比1/4还要小，就是这个讲。我们是为了要降低那个摩擦功率，因为你那个边边的宽度越宽，你的那个产生摩擦功率越大，所以你要减少功率。But in the normal situation, you can follow this guideline in your design. So when you decide when you want to determine your language, you can follow this guideline. So it's equal to the quarter of the length. Okay? So you can see this example in your page 53 and 54. So this is usually applied in the hydrostatic bearing because for the air bearing, normally we design the air bearing without preset. Okay, so you don't need to consider the language ratio in this case. So 我们刚刚风油变这个 自热应力的编程，通常是用在气压轴。气压轴跟一般我们的设计没有油枪，所以跟规则是没有。Right. So this is some comment for the engineering. Right. And here we have another criteria for design. When you design the high-speed reset bearing, you have two keywords, high speed and reset hydrostatic bearing. 高速而且是有油枪的这样的。So the guideline for the language ratio for high speed hydrostatic bearing, we still follow this one. In normal situation, we just using this language equal to a quarter of the length. Okay. 还是一样用这个，除非有特别的状况。设计完你去分析，又发现它的摩擦空间特别大，所以就把它的风油面再减小。那如果是正常的状况，我们还是用这个来设计。Okay. So this is the first design guideline for the hydrostatic bearing. So how you can design the language. And we have another, of course, this is only theoretical discussion. So we have an optimized viscosity data for the high-speed bearing. But in normal situation, usually the viscosity is not on your choice. Okay? The viscosity is depending on the rotational speed in your operational status. Okay? So this is only the theoretical discussion. You can find the optimum viscosity for high-speed bearing. This is not the case in practical application. 那通常这个只是理论上的看法，粘度是你不能选。理论上当然你可以用这样分析，可以分析一个最佳粘度，但是油的润滑油的东西通常是油品厂商决定，你不可能算出一个最佳的粘度，但是你市场上买不到，所以这个通常这个不是这样子决定。因为理论分析通常都是没有任何的限制，但是实物上的设计的话，就是你要找得到这个润滑油的粘度，但是有不同等级。This is just for your reference. 一般来讲，就是我的粘度通常是看我的操作转速决定。有的速度越快，有的摩擦功率越大，产生的摩擦的热就越多。速度越快的话，我就只能用越稀的粘度越低的，它就转得快。 Okay, we take a break and we discuss next for the optimum frequency for the high speed area. So we continue for this. This is also another design objective for optimum clearance for the high speed area. So because for the high speed bearing, the total heat generation will be tremendous. So the clearance should be larger than the low speed bearing. But this is also a theoretical study. So you can find an optimum clearance for your high speed area. But in practical, you cannot choose clearance as you wish because if you have a large clearance, which means you have a very low stiffness for your system. Okay. So usually the first paragraph is correct. The clearance usually is choosing with the assembly purpose. Okay. The worker can can manufacture the area using your chosen failure, then it's good for your design. So you cannot choose a very small failure because you need to discuss with your manufacturer, see if the worker can make the final assembly for the bearing system in this small failure. Uh, so in practical application, this is not applicable, so we cannot find an optimum failure as we wish. Uh, this is a fact usually you need to consult with the worker to do the final assembly. 一般来讲，轴承的间隙不是你想决定多少的当然，我们的轴承的话，它是有一个叫做刚性的东西，刚性会跟你的间隙大小有关，间隙越大的话，刚性越小。所以你要维持你系统需要的刚性，又要让那个组装的功能可以把你的轴承系统组装出来。所以最后决定这个间隙的话，通常你还是要跟加工厂的老板去讨论一下，这个到底可不可以组装？因为如果间隙非常小，就非常组装非常困难，组装非常困难的话，基本上就很难做。而且我们一般这个来讲，现在如果是一家楼的话，其实都要跑那个有限元素分析，看那个热温震到底会不会让那个间隙太小的间隙的话会摇这个其实都要经过分析过才能去做决定，不是像我们这边讲的， 可以去选一个最佳的间隙。所以他这边也有考虑，selection of the basis of tolerance is not always possible, particularly for the viscosity fixed by the requirement that of the hydraulic unit machine. 这个是 this is the formula you can obtain the optimum figure for sharing design. Okay. And another one is to discuss the optimum power ratio case for the high speed server. So this is from the research result. So Optis shows that by varying the viscosity increases, the total power can also change approximately 50%. Okay. So this is for high speed power, high speed hydrostatic bearing. The result of the optimum power ratio will lie between 1 and 3. 这个是他们做研究出来的结果。对高速轴承来讲，功率比的话，大概是落在1跟3之间会比较好。不过大部分你都不用担心这个。我们现在看到的低压轴承的应用的话，基本上都是在低速轴承的应用，高速的基本上没有。那气静压轴承的话，根本不用考虑这个热风跟摩擦功率的问题，因为我的气静压轴承空气排出去，它其实会把你的热带走，除非你的轴承系统是转速在30万转以上，你才要去考虑一下这个问题。所以这个其实我们有一些参数不是你能决定的，像那个粘度，for the viscosity, this was defined by your operational speed of the bearing. Okay? So usually you can take reference from the commercial product. And for the clearance, this was decided by the manufacturer. 所以这个间隙的部分也是一样，还有分析的结果，可能是跟制造的组装能力有关，跟分析的结果有关。我在高速的时候看这个间隙会不会很高，因为热膨胀会让间隙变小。所以这几个基本上不太能够决定。我们刚刚能决定的就是我们的一开始风油边，风油边可以决定。嗯，那当然我们这些热气变数其实互相之间会有影响。我们现在讲到现在都是间隙，油的粘度，风油边的宽度。那这边他教你怎么去取舍它，因为我们有时候去选风油边的宽度，就会影响到其他的参数。Okay. So here we have some general discussion about how to design the decide determine the design parameter of the hydrostatic barrier. So to reduce the temperature rise, it's better to reduce the length of the area rather than increase the freedom. 所以为了要降低温升的话，通常我们就是把风油边的宽度减少，而不是去增加轴承的间隙。轴承间隙增加，你的刚性就变小。所以第一个策略就是要减少风油边。当你决定了其他的参数之后，还是觉得温升太高，温升太高的话，就是把风油边，刚刚我们讲0.25变得更小。So this is the general rule for you. To reduce the temperature rise, it's better to reduce the bandwidth of the barrier rather than increase the freedom. Okay. Next, if you decreasing the viscosity, you have two results. So because shear is reduced and the relative change of viscosity with the temperature is reduced. 所以你选粘度比较低的油的话，就是它的剪切力，粘度的剪切力降低，而且它的温升也会降低。So this is another general rule for you to determine the design parameters in hydrostatic gas. And then the third one is there is a practical limit to reduce the length. 他说这边其实我的风油边减少的话是有一个下限。So the bandwidth should be greater than the 100 times of the film gas thickness. 这个风油边的宽度要比我的油墨间隙大100倍以上。这是它的规则。另外一个我们关切的点就是风油边如果太小的话，就是其实它风油边就很容易撞击的话就很变形。就是 the second one. There is thin members are vulnerable to the damage. 那还有下面一个。The most critical parameter governing flow is the bearing gas. 就是我们其实跟流量最有关系的部分，在一定要轴承来讲，是间隙的大小。如果轴承设计流量太大，其实要去减少油墨间隙，但是油墨间隙减少太多的话，就会让组装非常困难。所以这个你的油墨间隙如果是最后出来的大小，通常我们还是要跟你的加工厂。通常一般来讲，大部分都会在15mm以上。有啊，如果是有特殊比较小的轴承，还可以到10到15mm。如果大部分中大型的，都是会超过15mm。对。 There's another rule for the minimum gap or flue gap thickness. The minimum gap should not be less than 10 times of the average velocity for the various surface. 这个还有个规则就是我们间隙，油墨间隙的话，必须要超过10倍以上的表面积照度，高度表面的最高度。So this is another rule for design. So you need to read the text carefully for the discussion of the design guidelines in page 56. So this summarizes from page 56 some design guidelines for the hydrostatic bearing. And then we have a discussion for the optimum pressure ratio for high speed bearing. For the low speed bearing, mostly the optimum pressure ratio is equal to the 0.5, which means the research pressure should be half of the supply pressure for your hydrostatic bearing design. 对大部分来讲的话，在低速轴承来讲，或高速轴承都一样，我的压力比，也就是说我的油浆压力跟我的供油压力之间的大概会等于那个贝塔大概要等于1点，低速轴承和高速轴承。So this beta equal to 0.5, this pressure ratio is linked for the maximum load in most of the case. 通常会让我们的负载是最大化，这不是设计上常常会用，怎么去决定我的供油压力跟我的油箱压力的设置？这个我们常常会用到，我的供油压力跟我油箱压力之间，去决定，当然就是用我的节流器去决定它的压力要降到供压的一半。当然这不是我们随便说的，这是人家。So this is the result from the previous study for the hydrostatic bearing. So if you have pressure ratio equal to 0.5, normally you can result in the optimum or maximum load capacity for the bearing. 所以通常就是你如果是这样的设计的话，你可以得到最佳的负载，最大的负载。Okay. So we have an example in page 57 of giving you a hydrostatic bearing operator with minimum power. We have a pressure ratio and supply ratio and flow factor, viscosity, length and area. reset area, that edge, reset that sliding speed. Okay. For this, you can calculate what we are going to calculate the film gap thickness. This is how we want to calculate the film gap thickness for the design. Okay. For the next is the speed parameter. Speed parameter SH. This was applied in the hydrostatic bearing，这是我们平常用的速度参数 SH。当然 SH 有一个最佳值，所以我们这边的 SHO。那这个的话就是 this is the result of previous application。这是作者的，这个是作者之前发表的研究论文里面摘录出来。So the use of design parameter SHO for optimal design is optional. In this optimal design, SHO can be achieved simply by ensuring friction power equals to the pumping power. 所以这个 SHO 是从这边得出来的，其实是从他们1969年发表论文里面记录下来。So the next section in this, the next content for this section is that we classify the design parameter for the hydrostatic bearing into two groups. The first one is duty variable, the second one is the right variable. 所以我们这边把我们的这个一件合同的设计变数分成两大类，一个是功效有关的变数，一个是那个计算出来的变数，就是衍生出来的变数。什么叫做功效有关的变数？So the duty variable related to the bearing duty requirement, speed, size, application, viscosity, and material. 就是这些轴承跟轴承功率有关的相关的参数，轴承的短度、轴承的尺寸、公压、间隙，还有粘度，这个就是我们的功率的变数。So the duty variable are decided initially and adjusted later as necessary. 就我们一开始是会把这些先定下来，那如果是后面计算发现不行的话，还可以去做调整。就像年度一样，通常我们的转速，有时候可能要运动的速度知道，大概就可以把转速定下来。定下来之后，我们最后去算那个摩擦功率这些东西，再去看看年度这样子会不会发热量太多。如果太多，我们就去调整。设计就是这样的，我们有一些参数要先定下来。就像我们前面跟大家讲的，那个风油边。So the guideline to define the length ratio is equal to the quarter of the length. And for the derived variable arises from the optimum performance and the bearing shape configuration. So the derived variables include length ratio, pressure ratio, power ratio, and the friction area factor. 所以推导出来的变数的话，通常是跟轴承的能效有关，还有轴承的形状考量有关。所以我们有哪些是这个 direct variable, length ratio, pressure ratio, power ratio, and the friction area factor. 摩擦区块的常数。像 duty variable usually will be defined beforehand。通常的话就是跟风向有关的件数的话，我们预先就把它定下来，然后再去求其他的变数。除非是我们的性能分析发现有问题，才去调整。调整我的粘度啊，调整我的间隙啊这些东西。不过间隙的调整跟那个粘度的调整，通常是不太能够调整，要去考虑蛮多东西。So this is application for minimum power criteria. Application is ranging from 1 to 3. And we can have this formula such as KHP. And for this, we can obtain this speed parameter for the different signals equal to this. So this is for the plan bearing test. 就是这个是没有油枪的一气压轴，它的速度的参数是这个 stage。那一般来讲，我 usually before in the early 80s, 70 or 80, usually the computer is not so powerful enough, and therefore for the design of hydrostatic bearing, normally they are using the design chart. Okay? 通常 在70或80年代，1970或1980，电脑没有那么性能没有那么好的时候，通常我们做一些设计的话，都是用图表、查表法来做设计。这个当然就是我们去把它计算出来，把图表画出来。像这个就是没有油浆的轴承，那我们这边有不同的曲线，正方形的油枪，长方形的油枪跟圆形的油枪。那我的风油边的A 我们来了，比较这边的话是我的数据常数，3.9。那如果我的 K 是等于，然后我的 ratio 等于0.1，我们就用这个来查表去做计算。就以前的话就是这样子，不同的轴承形状，查不同的表来做设计。因为如果用电脑去算的话，就是你要算很久，所以他们就是先去把那些数值画成那个图表的曲线，我们就直接拿这个表来查表做计算。可以看到那个60年代、70年代、80年代那些的教科书在做一些低压轴承的设计，都有很多这种图片。So the bigger one is the optimum value essential, and the variation of the length distribution for circular head, square head, and rectangular head。这边有定义的，什么叫 rectangular head？ 这个长宽比是10倍，这个叫做 rectangular。那这是 so this is from the page 59. You can see how we can calculate the different notations here. AS bar. Here we have a B bar and AS bar. We also have the B parameter for the zonal bearing, isostatic zonal bearing. This was indicated in the bottom of page 59. The equation 3.19a, 3.19b. And this one is for the oil isostatic zonal bearing, and this one is for the aerostatic zonal bearing. So we have speed parameter for the thrust bearing, and we have a speed parameter chart for the zonal bearing. Okay. For the zonal bearing, we have recessed zonal bearing and planned zonal bearing. 就是有油箱的跟没油箱的，这个是有油箱的 recess plan 就是没有油箱，这是轴紧轴紧。没有油箱的通常就是气体压轴用的。 有油箱的通常就是1:3按照画在同一个表上。那一样，我们对刚所画的就是 power ratio 是 K 等于1，然后的 pressure ratio 是1。一样，我算这个 SHO 也是用差别，我用我的 language 去查。So here we also calculate the 50 variable. For the optimum. So we have the example in page 61, example 3.2 to calculate the essential for the two-step Kelvin variable. So we have some discussion for use some optimum heat length. So next topic we want to discuss the temperature rise for different varying speeds. First we look at the table 3.1. So this one is incorrect. This one should be eta. Eta is the viscosity of the liquid. This is not the H. 这个书上有印错。And the second one is the film thickness. And this is the language ratio. Okay? And this one is the thickness. This is the pumping power. This is the friction power. This is the total power. Total power is the friction power plus the pumping power. And K is the power ratio. friction power divided by pumping power. So this is the indicator for the low speed or high speed. So K is greater than 1 is the high speed. If the K number is bigger, that means it's in a higher speed. Okay. So we have 5 different designs. This is, this is just a table to show you how the design parameter will influence the friction power and pumping power. So we can compare this, maybe you should compare the same film gap thickness, this one to this one. So we reduce the language ratio from 0.25 to 0.06. So the film gap thickness is fixed in two. And then you reduce the language ratio, so the friction power will be reduced significantly. So this one, we see the friction power. This one, uh, the viscosity, you should fix the viscosity of the milk. So maybe you should look at these two. You just change the so the viscosity of the lubricant is 91 and 95. So the film gap thickness is the same, but the bandwidth is different. So we compare with design 1 and design 5. Okay? So we reduce the bandwidth ratio, and you will have very small friction power from 4.26 to drop to the 2.25. Okay? 所以你比较这个表，然后它这个设计参数，你每次改变一个参数，你就可以看它的效果。You also can compare the design 1 and design 4. You're using the same viscosity lubricant, and the film gap thickness is changed to the from the 13 micron to 32 micron. Okay? So we increase the clearance in this case. So the stiffness, this one is the stiff, will drop significantly. So from 180 drop to 75 and 73. So by using this numerical table, you can see individual parameters, how each individual design parameter will affect the performance of adjusted variance. So 我们就可以看从这5个不同的设计，改变一个参数的话，设计参数，它对轴承性能的影响。 For the high-speed variant suggested by the author of this book, it's better to design the high-speed variant with a power ratio ranging from 1 to 2。这边是这个我们这本书的作者建议的，高速走诊的话，当然这是他们研究的结果发表出来。如果要设计的话，功率比是在1:3之间会比较好一些。但是其实也不用担心，在市面上或是在工业应用，大部分的一阶压轴承都是低速，基本上大概95%以上。那你如果要用高速的，就是它的功率比更大，就是速度更高的话，通常你要用没有油枪的一阶压轴那你就可以用那个3到9。我们讲的都是讲一阶压，空气轴承完全没有限制。空气轴承因为是那个空气的粘度比油来讲小1000倍，再加上我们的空气是一直飘散到大气中，它把热带走，所以空气轴承基本上，除非你是30万转或50万转以上，你才要去好好的考虑功率的问题。一般来讲，只要不是30万转以下的都不用考虑温升的问题。好吧，我们这一章介绍完。Any question for today's lecture? 第9周我们会期中考，我们下礼拜会教到，下礼拜会把第4章教完，所以期中考是考第1章到第4章，你这样欧洲会。对，第9周就是我们期中考那一周，我们会有欧洲这个考试，好吧？如果没有问题，我们就下课。See you next week.